Thank you very much for everyone joining us today. My name is Adam Carroll. I'm a senior engineer at Oak Ridge National Laboratory and chair of the ANS Robotics and Remote Systems Division. I'm excited to serve as a moderator for today's second installment in our webinar series, Nuclear Robotics and Remote Systems Highlights from University Partners. Today, before we get started, I would like to cover a couple quick notes regarding today's event. If you have any questions, please type them into the Q&A function. I will attempt to address as many questions as I possibly can. The event will be recorded, and a link to the recording will be emailed to event registrants by tomorrow. Additionally, certificates of attendance for the event are available for ANS members by request. Please see the chat for contact information. And finally, we ask that everyone respect the ANS Code of Ethics and Responsibility, Respectful Behavior Policy, which can be found at ans.org. With those notes out of the way, I would like to introduce today's speakers. We are fortunate to have YZ with us today. He is a professor of engineering physics chair in the Department of Nuclear Engineering and Radiological Sciences, Department of Electrical Engineering and Computer Science, Department of Material Science and Engineering, Department of Robotics, Applied Physics Program at the University of Michigan. We also have former RRSD chair Leo Lagos with us. He is the Director of Research at Florida International University Applied Research Center and principal investigator of a $24 million 5-year cooperative agreement between the U.S. Department of Energy and FIU in support of DOE's Environmental Restoration Program. And last and not least, another former chair of RRSD, Mitch Pryor. He is a research professor in nuclear and radiological engineering at the University of Texas at Austin and is the co-founder of the Nuclear and Applied Robotics Group and RAPID, an industrial affiliate program supporting automation in the energy sector. All right, today we're going to start with YZ, and he's going to give us a presentation on his robotic research. I'll turn it on over to YZ.
Okay, good afternoon, everyone. Thanks for the introduction. Can you see the slides? Is it good?
Yes, it looks good.
Okay, awesome. I'll get started. Thank you for the invitation and warm introduction. It is my great pleasure to be here to co-present with Professor Lagos and Professor Pryor. So I'm going to talk about some soft robots we built in our lab in the last few years, and hope to use this talk to stimulate some discussions on the use of advanced robots for extreme environment applications. For my name in case you're curious, my YZ is just my real legal name with a single letter Y as first name, single letter Z as last name. To get started, I want to thank a number of my awesome students who have been doing the work. The robot I'm going to show are mainly built by another student who has graduated, is now shown here, Long, and later David, Kevin, and Kelsey. So, and our robotics work is mainly sponsored by NSF and DOE Fusion Energy Science. All right, so without further ado, let me get started. So very quickly, I usually summarize the research carried out in my lab within 2 words: matter and machine. So half of my research is really on the matter or material side. We study far from equilibrium statistical physics, mostly in complex material systems. We still have a lot of ongoing effort in this direction. This is not something I'm going to talk about today. The second half of our research is really on robots and machines. And the overarching goal of our research on robotics is to develop robots for extreme environment applications. Roughly speaking, we build 3 kinds of robots. The first one is related to soft robots and human-compatible machines. So soft robot is one of the emerging field in robotics in the last roughly 10 years also. We have done a couple work related to that. This is the main focus of our talk today. In addition to that, in the last 2 years also, we have also been getting into another two areas. One is swarm robots. The second is wheel-like hybrid robots. I'm not going to spend a lot of time on that. Maybe I'll show just a couple videos toward the end on this too. All right. So robots. Robot itself is not a new concept. Humans have been dreaming about robots for several centuries. At the very beginning, what we had hoped for are like this. So it could be like general purpose Android that are even more human than us. And we dreamed about having crazy robots that can kill us all. And we also dreamed about an obedient robot that can always help us. And lastly, the cute, harmless body. So robot itself is not a new concept. However, this is what we have now. This is probably the most commercially successful product we have now. Nothing like the robot we imagined. So although we do admit that these robots vacuum are helpful at home, perhaps we can do better than that. So like why clearly there's a gap between the robots we dreamed about and the robots we have now. So why is that? If you think about the pros and cons of traditional robot, I like to summarize here. And from on the pros side, the traditional robots are very precise, very powerful, very reliable. But on the other hand, they are usually made of metals. They are very heavy and they're very dangerous. When they fail catastrophically. They also consume a lot of energy and they are very expensive. And for those reasons, for traditional robots, they are usually kept in cages. So one of the motivations to build robots with soft materials is to free these robots from the cages. Now, this is the main topic I'm going to talk about today. Like, can we build soft robots? Can build robots out of soft materials? So the so-called soft robots are made of advanced soft materials. And here are like three movies that we built in our lab. The first one is a soft actuator, pneumatic actuated. With these actuators, we can build grippers even without sensors, one sensors or feedback. They cause a little harm or no harm. And the last little movie shows we use conducting polymer and to when you stress the polymer, the rubber, the resistance change, we can use that as embedded sensor. So in our lab, we explore a lot of soft materials to see whether we can build robots out of those soft materials. And the obvious advantage of soft robots include they are inherently safe and they are flexible. Compared to metal, they're also very lightweight. They're so light that you can even wear them. They consume very little energy. And lastly, they are usually very cheap, disposable technology. So soft robots has been a emerging topic in robotics field for about say close to 10 years. And initially, the soft robots has been developed for like agricultural applications like fruit, vegetable harvesting, and there are obvious applications for healthcare, medical applications, and we can wear them. So there have been not a lot of exploration of soft robots like for nuclear application. This is where we came in. Okay, so let me show you like one video of the soft robot arm we built initially. So this is a three-section, three module soft robot. Each of them is actuated by three pneumatic actuator. As you can see, even with the three component, with three modules, the degree freedom we can achieve with the soft robot is already beyond what we can do with the traditional robots. So this work was done a few years ago, and we filed the patent. And later, we thought about like many of the soft robots are inspired by the soft animals in nature. And if you think about the soft animals, the purely soft animals are mainly found in oceans. So later we converted this pneumatic soft robot arm to the underwater version. When we convert to underwater version, with the hydraulic actuators, we can provide more power to the robot. In addition to that, you can tune the density of the robot to be close to the water. Then the weight of the robot itself will not matter that much compared to the in-air version. So this is a movie to show this underwater version of the robot, self-robot we built. Okay. So the scale of this robot is kind of like our arm, and we build more modules. We have 6 modules, and at the end of the arm, we also attach the grippers. And those actuators are driven by pumping water from the environment. In fact, if you look carefully, you might be able to see some of the bubbles here, like, indicating pumping water from the environment. So let me show you a speed up version. So this is the fast version of the movie with the 6 sections plus the grippers. You can see the amount of degree freedom we can achieve. It's a lot more than treating robot. It can even go around obstacles and grab things. This is kind of to simulate a reactor pool applications. And so this is another movie to show that if you want to grab some object around the obstacle with traditional robot, then you really need to have multiple sections, which is doable. But with soft robot, then even with like a short arm, we can already go around this obstacle and grab objects. And that opens up a lot of novel applications. So if this robot arm sounds or seems familiar, and indeed they are inspired by movies. So like we draw inspirations from a lot of movies. This is a Dr. Octopus. So interesting, you see the arm we built is almost identical to the arm of the Dr. Octopus, except that our robot arm is made of soft materials, like no humans can carry those metal arms. In other words, our goal is indeed to build the soft Dr. Octopus. Interestingly, if you recall the movie, so Dr. Octopus designed and built these robots in order to make a fusion to happen. And this is exactly what we do in our lab as well. So we want to build robots for nuclear applications. So those are the demonstrations, and there are still a lot of work to be done, like behind the scene. For example, the simulations control and the materials. So in the last couple of years, the main thing we have been focusing on the simulations and control platform for soft robots. So soft robots is relatively new. So it doesn't have as many like a CAD software as a traditional robots. Well, luckily, we are in the nuclear field where of MOOS. So MOOS provided a foundational framework to do high performance finite element simulations. And we made use of MOOS, but MOOS is not built for soft materials. So with on top of the MOOS environment, we implemented a hyperelastic deformation so that we can simulate the large deformation of the soft materials. And we implemented the dynamics, because in soft robots, the dynamics or kinetics is very important. Lastly, we also implemented efficient soft contact mechanics so that we can simulate the bending of the actuators because of the contact. So it's very quickly, I'm going to show you a couple of demonstrations. So here we build a very simple hyperelastic pendulum. It's the actuator we use in the soft robot. And of course, it's a chaotic system. We cannot fully simulate the trajectory, but the spectrum from the simulations and the experimental data agree pretty well. And here we show our platform can also simulate these vibrators, elastic vibrators of the actuator. And lastly, is a simulation of a two-dimensional soft arm because of the contact the soft actuators to cause a bending of the actuator. And here, like another 2 demonstrations to show the effectiveness of the contact mechanics. This movie shows that we can now simulate the gripping of actuator and hold this object of some irregular shape and leave it off the ground. So that's the simulation side. In addition to that, we also worked on the controls of the solve robots. So the control of solve robots is very challenging. We cannot, because the deformation of the robots are continuous. So we really cannot use the traditional control theory control the motions. So in this paper, we used a new method called automatic model predictive control, auto MPC, which can automatically tune the hyperparameters for the MPC. Then we compared our controllers with a number of other controllers like CQL, TRPO, etc. I'm not going to show the details. And we use the controller to control the robot. This is two-dimensional version of underwater robot to control robot to reach certain target. And we show auto MPC outperforms the other controllers. Okay, so like soft robot is the main direction we've been working in the last few years. For next two slides, I'm going to show you some new directions that we take in our lab. And one of them is swarm robots. So swarm robots related to like a large number of robots, and collectively they can accomplish tasks difficult for individual robot unit. And this is inspiration from like CookieBot from the Minions Despicable Me, and also Microbot from the Hero 6. So we build in our lab, we build this vibrator-based robot. They're very cheap, and they are not even run on wheels, but we can build many of them. Look at the collective behavior of these robots. And now we can control the individual vibrators and also control the local motions of the robot. Since they are very cheap, then we can, and also very small, we can, on top of the robot, we can install sensors and use them for information collection. And the third type of robots we built in our lab is the so-called wheel-like hybrid robots. There have been a lot of interest in like a quadruped robot like Boston Dynamics Spot before. But light motion is not as efficient as a wheeled motion. And so since the beginning of last year, we began to build a wheel-like robots. And so interestingly, about roughly half a year since we started, like last summer, Unitree released a version of this robot. They are ahead of us, so we need to catch up on this wheel-like robot system. Okay, so in the interest of time, I'm going to summarize. So I want to conclude with this quote from Tao Te Ching. And I think this really summarizes best why we are interested in soft robots. So Lao Tzu said that the soft defeats the hard and the yielding conquers the strong. So usually when I think about the soft robots, we think that maybe they're fragile. They are not useful for nuclear applications. But on the contrary, soft robots are actually very good for nuclear applications because of their metal polymers. And even if they are going to fail, and everything's going to fail with the very strong radiation, soft robots is no different. But because of their metal polymers instead of like semiconductors, then when they fail, they don't fail instantly. So they are going to become hardened over time, and we can change the controller to adjust based on that. And eventually, the soft robot is going to fail, then we can replace them. The robots we build are modular, and they're made of very cheap materials. So that's why I want to conclude that maybe we can think about soft robot and use them for nuclear applications. So in summary, like advanced robots such as soft robots, swarm robots, hybrid robots may hold the key for the nuclear renaissance. Okay, with that, I'll stop here. I'll be happy to answer any questions you have.
Thank you so much, YZ. That was a very interesting presentation. We got a few questions, and I think we have a little bit of time to answer some of them. One of the questions was, because the soft robots is such a new concept, I take it you pretty much have to design all new finite element analysis and simulation tools in order to really be able to figure these things out.
That's right. So it's relatively new. It's not as new as 5 years ago, 10 years ago anymore. And there's a large enough soft robotics community. Like it's big enough. There's a conference called IEEE RoboSoft, in addition to like ICRA. So that's a standalone community. Uh, but you're absolutely right. And there's a lack of a standard in soft robots. Everyone has to design their own robots. And in the past, there were really not a lot of simulation tools that one can use. That one of the reasons that we decided to build on the simulation control platform because there was nothing available. There was one, as a plugin from I think plugin called SOFA and developed by Europe, and we try to use that a little bit. And it's designed for soft robot, but cannot simulate like hyper-elastic deformations and still treat materials as a elastic material. And that's the main reason we decided to build our soft robot simulation platform, which we call Kraken. Just like many of the most applications, that's animal name, and we call our simulation platform to be Kraken. And still a lot of work to be done in this area.
One other question that came up, is visual representation feedback the best way in order to kind of create a control feedback loop, or have you tried other sensors in order?
That's a very, very good question. This is it's not a question that we can, it's not a problem that we can easily solve. So that's why when we try to develop new controllers, we use a two-dimensional version. With 2D version, it's very shallow water, then we can still use cameras, visions, and provide feedback. Indeed, like one idea we have is, as I showed at the beginning of the talk, we try to embed some sensors in the software robot, like for example, conducting polymer. Then we can, based on the resistance of the conducting polymer, we hope we can infer the configuration of the robot. Then we can use that for control. We are far from there. And if we move on to three-dimensional robot arm, it's even more challenging and depend on visibility of the water. We can, so far we only tested on the very clear water, but still a lot of work to be done. Very good question.
All right, well, I think unfortunately that's probably all the time we have for questions, and we'll have to turn things on over to Leo. I do appreciate all the people who have submitted questions. I apologize that I was only able to get to a small portion of them.
Yeah, thank you, Adam. I'm happy to connect with the audience offline. Feel free to shoot me an email.
All right.
Thank you.
Thank you very much, Boise. All right, now we'll turn this on over to Leo for his presentation.
Great, and I think Dennis going to help me with the slides. So, yeah, Leo Lagos, Florida International University, Miami, Florida. I'm an associate professor, College of Engineering, also director of research at FIU Supply Research Center. So, besides my contribution to the work, obviously we have full-time staff and my colleagues. I have a couple of names there, Anthony Abrahao and Mackinson Talusma, but there are many other colleagues that work in the robotics lab, as well as students, PhD level, masters, and undergrad. So we typically have about anywhere from 15 to 25 students doing various research. If you can go to the next slide. Just a quick introduction of FIU. So Miami, Florida, it's a public university, so it's large. It's really a South Florida area, about 58,000 students, and among one of the largest Hispanic serving institutions and school, and we do research, right? So we have PhD programs in all disciplines. So we are currently R1 type of research institution. All right, so if you can go to the next slide, then a lot of the work that I'm going to present here is very centric to the DOE Office of Environmental Management and Office of the Legacy Management. So really dealing with the back end of the nuclear cycle, right? The decommissioning of facilities across the U.S. And also once those sites has been cleaned up, they get turned over to the Office of Legacy Management, and they will continue monitoring those sites for many years to come. So in terms of the OEM, obviously their mission already 30 plus years in managing the various sites across the U.S. I think the number was over 120, 130. Now that we're down to, and I say we because we've been helping the Department of Energy on this for a very long time, since the Applied Research Center was established. But we're down to about 16 of them, but those are the ones that present the most challenging aspects in how we're going to decommission those sites. So besides using the humans, obviously we're going to have to come up with better tools, better technologies, and better mousetrap to be able to really address those really unique problems. So that's what we do at the Applied Research Center at Florida International University. And also we are helping the Office of Legacy Management of the stewardship of those sites for many years to come. So next slide. So based on that, what you see there is really a compilation of the technologies that we are actively working on. And you see a 5-year period. That just the time of our cooperative agreement with the Department of Energy is in 5-year cycles. So this cycle ends this year at the end of 2025, September 2025. But within those 5 years, we have worked on a number of technologies. You see little check marks in green. That means those technologies have been developed in the lab, fully tested, prototyped. Also have we have sent those technologies to the various DOE facilities. You see some of those names on the column on the left, and for a on-site testing, whether it's a cold test at the facility or an actual deployment of that technology in a specific problem set, and I'll show you a couple of examples of that. So the green mark just signify that those are kind of the end, the road for that technology in terms of the development, and then those prototypes can have been demonstrated at a DOE facility to the actual companies, the contractors that are performing the work. So the first one you see there, I'll show that example, is the mini rover, one of a kind really, in terms of the size, very small, that will go underneath the high-level waste tanks that contain at the Hanford site. And the second one is the lateral gamma. That's for a single shell tank, also at Hanford. And the off-riser sampler, that would be a robotic arm that would go inside the tank to collect samples of the waste in the tanks. And above grade, right? Above grade is we have another system for long-term surveillance of the facilities that manage those tanks. That's Hanford, all the infrastructure above grade that support the mission. Then I'll also show an example of the H Canyon. That's Savannah River in Aiken, South Carolina. Another problem set, very unique, the H Canyon, and I'll speak to that. We have also developed robotic platforms for the waste isolation pilot plant. That's a repository, which is a salt mine in New Mexico. So we are working on technologies to, characterize and do 3D scans of the salt mine. And also have done some aerial using LiDAR and different types of drones. And the last example that you see there, I guess I think it's cutting off, but a couple more that you see there. One for the LM, legacy management. That's a robotic platform that uses a ground penetrating radar to see any defect in the waste disposal cells. Because of time, some of those cells are eroding, and we need to inspect those cells. And I think the last one that I don't see, but is there on the slide, is exoskeletons, using wearable robotics to help the DOE workforce in their routine tasks that they do at the various sites. Next slide. So the first example, I'm only going to show 3 or 4. Hanford, the tank farm, there are the double shell tanks and the single shell tanks. The original tanks built in the 40s and 60s are the single shell, right? Only one shell, metal, is carbon steel, holds radioactive waste. And then the newer tanks, really built in the 80s and to the late 80s, 28 of those are the double shell. The first shell is a carbon steel, Then there's a space between the first shell and the second shell. The second shell is concrete, and the space between the two shells is called the annulus, and that's a way, an access point where those things can be inspected. This is outside the tank. Inside the tank, obviously, you have to go through the risers, which are round pipes of various diameters, and you can insert different tools to understand the the composition of the waste that is there, and monitor the solid and liquid interface. So the reason I'm mentioning this, because to inspect the bottom of the tank, underneath the tank, very small spaces, ventilation pipes and cooling channels, refractory slots. So that's underneath the metal shell. And there are a number of pipes and channels that you can use for inspection, but it's very small. And if you can go to the next slide, this is a in-house development. It's called the Mini Rover. We developed that at FIU. We also patented this technology, and the purpose was to be able to go through some of those small channels underneath the tank and look for any signs of corrosion or radiation, anything that you can see. This only has a camera and a video camera and a camera. So this was just a tool for inspection. And it has obviously a control box that we developed, the actual tool that you see there, printed in metal, 3D printed. And if you go to the next slide, it shows the in-house testing that we developed, or the mock-up really that we developed at FIU to fully test the technology, right? So what you see on the bottom right is a mock-up of a section of the double shell tank. I mentioned the concrete outer layer, which is the outside shell, a space between that and the inner layer, which is metal. And also underneath, the video on the left shows the Mini Rover going underneath, which we also duplicated the piping system that is underneath that metal shell that you see on the bottom picture. And the video that played earlier was just exactly that, underneath the metal shell, which identifies or represent the metal portion of the tank under the tank. So fully tested at FIU, and once we have done that, then if you go to the next slide, you see a cold test that we did perform. Obviously, we are not allowed to to operate the system ourselves, so we have to train the workforce. Former WRPS, I think now they're called H2C, but those are the contractors that manage the tanks at the Hanford site in Richland, Washington. So we trained them how to operate the system in a mock-up that they had. And if you go to the next slide, it shows the actual deployment. Unfortunately, the left video doesn't show, but if you can play the right video, you'll see that the Mini Rover coming out of the tank. The left video that is not playing, it shows you the operators maneuvering the Mini Rover and driving that into those small slots underneath the tank. So this is the actual tank. The cameras that you see, they're already in the tank, those in the annulus section, and those can be retrieved from the top. So we had a successful deployment. This was March in 2022. Proved that the technology was able to go inside those very tiny slots, inspect the bottom of the tank. It's magnetic, so adheres to the metal surface, to the carbon steel of the inner shell of the tank. So that's an actual deployment of the technology. If you can go to the next one, next slide. I believe it shows a different problem set. The previous one is a double shell tanks. This is a single shell. The older tanks, there are 3 pipes underneath the tanks. They're called laterals. They're in a V shape. It's only one access point above grade. So they needed a tool that can go inside a pipe and again, inspect. So to get to the bottom of the tank, you have to go 70 feet vertically, then 140 feet on the bottom of the tank to be able to inspect, to go through all those pipes. So we have to do one pipe at a time. So survey one pipe, go back in, insert the pipe crawler to the second pipe and then the third pipe. So our solution, if you can go to the next slide, It's just develop a pipe crawler, an inchworm, which is, I'll show you in a second, but this one just shows here a mock-up that we did. The technology, again, was developed by FIU, and then in the summer, we had a call demonstration, and the company, they developed a mock-up that represent the actual the pipes that goes vertically and then horizontally underneath a single shell tank. That's the called test facility in Richland. If you can go to the next slide. This shows the two videos using that mockup. It shows the video on the right. The inch worm crawler is a pneumatic crawler which contract, expands, and it covers the entire length, the 240 feet. We also developed a synchronized reeling mechanism, so the whole operation can be done autonomously. Just typing commands on the computer screen. So the video shows going in, and then I think if you play the other video, it would show that coming out of the pipe. But again, it proves the concept that we can use that pneumatic crawler, and also it's not part of the system yet, but one of the modules would have a radiation sensor to be able to detect any possible radiation underneath the single shell tanks for this application. Another, if you can go to the next slide, another application I wanted to just showcase is the Hemford pit area. Those are, they look like pools, but this where they have all the connectors when they do transfer of the waste from one tank to the other. That area, obviously very high radiation. It has a concrete block, which is about 5 feet in width, I guess, or in the vertical direction. They're about 10 by 15 in terms of size, in terms of feet. When any operation maintenance has to be done, the concrete block has to be removed, and then people with PPEs have to go in there and either using tools that they have developed themselves, try to repair some of those valves or some of the pumps or whatever is inside that pit. So if you go to the next slide. They have done some preliminary work. I think Peter Griffin at WRPS have done some robotic manipulation. I think what he did, they were able to do some painting of the floor, if I believe. I might be wrong, but they did some previous operations using a robotic arm. I think it was a universal 16 arm. So they have done some work. So if you can go to the next slide. What we have developed at FIU is a system. I'm not sure if you can go to the next slide. A really handyman tool, a robotic arm mounted on a mobile platform that has pneumatics, uses pneumatics, and it can use different tools. So our concept was to be able to lower this platform into the pit, and then the robotic arm would choose what tool to pick for whatever job it needed to be done: grinding, cutting, spraying, any type of operation. So a handyman really to be able to manage all the different tasks that has to be done as maintenance of those pits. So this would go in the pit, will be lowered into that area. So you can go to the next slide. Though I think it's a video, if it just shows the concept in the lab. Obviously, we had developed the platform already, and then we using the universal arm, and they have a camera for perception. It has a lidar as well, so we identify which plane we need to work on, and then the robotic system would pick up the action, the tool that is needed to do the job. I think you can go to the next slide. Yeah, this is all the other problems that I showed you was Hanford site related. This is a different one. This is the Savannah River, the H Canyon. I believe Mitch might remember this one. We have worked, I think we worked together on this initially. We have continued working on that. What it is, it's just the reprocessing facility is connected to a ventilation system. This tunnel is a couple hundred feet long, 10 by 10 area, and it's only not non-human, humans cannot go in there, so it's all remote entry only. There's a picture of that on the bottom left. You see the 10 by 10 area, and the walls are deteriorating because of the nitric acid that passes through that tunnel. So if you can go to the next slide. I'll show you one of the concepts that we have developed. We started this with Mitch a few years back. Is a really wall crawler. So the idea was to be able to, send a robotic system into that tunnel, take the smaller system, on the bigger crawler, and then deploy this on the walls of that canyon and be able to do inspections. And the holy grail would be to do repairs. So we developed the wall crawler system. The wind that you see there, we just in our mock-up, we mimicking the 20 miles an hour wind that is in that tunnel at all times. And if you played the bottom video or the video on the right, um, it just shows you the same system that can not only do walls, but it can also do ceiling surfaces as well. So it goes 90 from the wall to the ceiling. So now I'm running out of time. So if we can go to the next slide, I'll quickly talk about a couple of systems we have for decommissioning. Obviously, the 3Ds of decommissioning, dirty, dull, and dangerous. So sometimes you have, instead of sending humans to do the D&D or decommissioning of facilities, we can use robotic systems such as commercially available spot mounted with LiDAR and be able to do 3D mapping and then 3D digital twins of the system of the area before we send humans in. So we have done some of that work. And I think if you can show the last slide, as I quickly wrap it up. It's just in our facility, just using the dogs with the LiDAR, collecting information to develop 3D maps, radiation maps, and also coupling this to the building information system BIM to be able to facilitate decommissioning and reduce the exposure of the workers to dangerous environments. So with that, I think I better just conclude here. Again, thank you, Adam and Daniel, for the invitation. And that's all I have from my end.
Thank you very much, Leo. I think we have time for a few questions. For most of your robotic applications, do you ever utilize commercially available rad-hard motors or sensors?
Yes, on some applications we do, depending on what it is. Again, for us, this goes to the prototype stage, proving the feasibility of the technology. So most of them would be 3D printed systems that we develop. But from time to time, we have had to have some rod hardening, sensors or other things to be able to deploy them.
Great, thank you. After you hand over one of these systems for deployment, do you ever get feedback or additional information from the sponsor on how things are working or questions or needing
Yeah,
repairs?
we continue. Yes, of course, we continue. As I make it part of their toolbox. Sometimes the same system can be used for something else. For example, of the mini rover that I showed that I went underneath the double shell tank, that was just inspection, right? But then when we did the inspection, we saw some white stuff there. So now we were interested. Hey, can we take a sample of that? So the next generation or the next iteration of that mini rover would be the same system, just having some vacuum system or some scraper that we can collect samples from underneath the double shell tanks. So yeah, we constantly are in communication with the end users in terms of improving or having the same technology do something else.
And I think the last question, we got this about 4 times. So for the robot that's climbing up on the wall, how is it doing that?
Yeah, it's just the action reaction. So it has the thrust, right? It's pushing one way, and then the reaction is pushing the rover the other way. So it attaches to the wall. It keeps that equilibrium. Obviously, you have to think about the momentum, but we have done all the calculations where we can keep it on the wall and be able to go up and down or side to side.
So it's basically creating like a thrust.
Thrust, yeah.
Okay. All right. Perfect. I think that's all the time that we have for Leo. I greatly appreciate the presentation. It was very interesting. All right. We'll transition on over to Mitch for our final presentation of this webinar.
Mitch, if you're talking, we cannot hear you.
Or if we lost him.
Yeah, I'm not seeing anything.
Looks like maybe will rejoin. I just saw him that drop off. All right, here we go. Well, we'll give Mitch another minute to see if he is able to figure out what's going on from a technical standpoint. Success. I can see you, Mitch.
Apologies. Can you hear me, Adam?
Yes, I can hear you.
Okay. Apologize. Zoom just decided to crash 5 times in a row. Um, so apologies. I missed the last 3 or 4 minutes.
Well, we're ready to transition on over to your presentation.
Okay, let's see what I can do, and I will try to make up time by talking fast and or short. Let's see how that goes. Some screens. Yeah, that was not great timing. And I was all set up, of course. Okay. All right. If you guys can hear me and we're on time, then I will try to just give you guys the quick 10-minute version instead of the longer version. But I am Mitch Pry. I'm a research professor here at the University of Texas at Austin and head of the Nuclear Applied Robotics Group, which I founded with my nuclear colleague, Sheldon Landsberger, in about 2010. We are a part of Texas Robotics, which includes about 17 faculty. We've got our own building here that is kind of at the center of the College of Natural Sciences and the engineering. So we have faculty from 4 different departments in this area, quite a bit of industry engagement, and a brand new building, literally an old gym that we can fit a bunch of robots into. Within that, the Nuclear and Applied Robotics Group has kind of some core competencies that are really focused originally on nuclear and then have extended into other hazardous environments as we've gone on and our group has grown in reputation. A lot of our work was with Los Alamos National Labs, the handling of special nuclear materials, autonomous radiation survey. I did some mobile manipulation work there, looking into their the basement there at PF4, autonomous scan and plan. For security, we did wall climbing robots, both for the oil and gas industry as well as for dry cast storage inspection. And then really trying to make these robots easier to use. A lot of work in the human machine interfaces, particularly around AR, to improve situational awareness. I'm going to give the briefest of briefest histories of nuclear robotics, as in I'm just going to fly through these pictures and see how many of you recognize various robots and robot items that have happened throughout the history of nuclear robotics. I would actually argue that a lot of robotics were really inspired by Ray Gortz because it was really the first industry that really needed them. And we've developed a ton of excellent programs, everything from the Air Force to handle things coming off of nuclear bombs, getting into reactors, 3 Mile Island, Chernobyl, Fukushima, taking that robot Mighty Mouse into White Sands. Great work that Sandia National Labs did that. Dual arm work module, the radiation survey robots that first kind of came out of Idaho National Labs. And of course, I can't even go into all the robots that you've seen already today, where even Leo and YZ have effectively doubled so much of this. But what have we really learned from all that is what I wanted to get at. And we see that there's definitely a lot of previous work in this area. Definitely work motivated by needing to get into these hazardous environments, but unfortunately, most of it has been done in silos. Over the last 30, 40 years, we have collectively reinvented a lot of wheels. The vast majority of the solutions are either teleoperated, a human is 100% in the loop, operating the thing remotely, sometimes even at the joint level with no additional burden of the operator reduced, or fixed automation, where a robot has gone in pre-programmed to do a particular task and does it over and over. We see that. And therefore, this is why robots continue to be slow, either slow to use because they're teleoperated, or slow to implement because every new task requires a new integration. And the feedback from one of our more recent horrible events, Fukushima, really showed that some of the challenges were the lack of field knowledge in the researchers. You know, a lot of the robotics folks that we want to work with don't know an alpha from a beta from a gamma. To understand when a robot is going to be necessary or not is an open area. A lack of precise communication between the researchers and the users. We tend to not be the ones who deploy the robots. It is, for example, the TEPCO employees or the users in these facilities. And therefore, there's a lot of education and training that is necessary. And then, of course, there's the decontamination. But the big thing is, we should have been using these robots the whole time. These robots need day jobs. If we save them for when we need them because of a hazard, then we will always be starting from scratch. I saw some emergency response robots at Savannah River. They trained up. Fortunately, they almost never need them. So the robots aged out. Folks learning them stopped worrying about the training. It's a hard thing to do. So let's give robots day jobs is my big theme on how we can kind of do that. And if we're going to give robots day jobs, then there's kind of three challenges I want to focus on today. That of scalable solutions, the multidisciplinary aspects of it, and providing situational awareness to people in the room, because one of the things that we are learning as robots appear more and more in society is that the people around them must have agency to interact with them. And that is the people in the room with the robots, not the people on the screen on the other side. So just 4 quick examples I'm going to go through real quick. The first one is radiation survey. This is work that we're doing for Los Alamos National Labs. We are actually deploying this summer. Our hope is to put a robot into PF4 and demonstrate the full heterogeneous team of robots working in the pet training facility there. Our approach really to this is to recognize that we need to solve the problems that go beyond just a robot collecting radiation data. Alpha, you obviously have to be within a 1/4 inch of it, and you want to be able to test in places that are hard to reach. So we use a small robot you see in the upper left to give ourselves a full 3D LiDAR map from an extremely low perspective in the room, and also to get robots back in and behind things. We use a standard lanthanum bromide robot that can fully autonomously use recursive Bayesian analysis to determine where sources may be when it comes to gamma and beta. And in the bottom left, you see a robot that has a large alpha radiation sensor that it can put up underneath tables and do it safely because it has a full map thanks to the small robot that's given the map. And finally, in the bottom right, not only do we use the quadruped robot to do alpha radiation survey on glove box and other surfaces, walls and things like that are not the ground, we actually use it to autonomously move things out of the way. So we move chairs and trash cans and things like that so that the other robots can actually do their job. It is those things that are necessary for the robot to be able to get done. And then, so when the robot comes out and it's actually doing its full survey, here you see our alpha radiation survey. We've came up with some particular navigation profiles that assure that the wheels never touch any place that the sensor hasn't already cleared of alpha radiation survey. And then when a radiation may be found, the worker is notified, and the worker is given full situational awareness of where the robot was working without having to go to a screen or walk up or interact with any device. You simply flip down the visor on your augmented reality. The sensor is not on the front of the robot right there because it was actually at Los Alamos, and she can immediately see where it's safe to walk, where the robot is cleared. She can see what robots on her team have been given what commands by who, what their location is relative to them. And then if the robot did trigger an event, you'll see her walk over to the left, and you can see the hot spot in the back of the room. So she knows exactly where the alpha radiation was found. And this is just a small little polonium source that we had in the room to be able to test with. So this kind of encompasses all of that. Give robots day jobs, and then those robots are there when you need them for an emergency, and give the people agency, and give the robot the ability to scale its solution to large spaces. One other example of where we're doing that is if we want robots to be able to interact with the environment, then we need to be able to rapidly teach them how. Here you see an example of Frank Riegel interacting with a door, and instead of recording the task, what we are actually doing is learning from that door what it affords the rest of us to be able to do. So it learns how the door works. And what that allows, as you will see in this next little bit, so I'm going to forward just a little bit, is that when the robot has been taught here by Frank what the actual interaction for that valve is, he's given it the same thing. It's learned how to interact with that valve. And then this robot can come in and interact with that valve in a way that allows it to turn it 40 degrees, negative 50 degrees, hundreds of times, and or to some particular pressure or something like that. So it's learned how that valve works. So this is one mechanism to scale. The last one is talk about how we are able to determine corrosion and other elements in a light invariant method using the specular reflectivity. And that allows us to autonomously go in and actually repair walls with no human in the loop. So when it detects corrosion, it knows exactly where it is, and we're able to either laser ablate, or in this case, we just use some spray paint to demonstrate the robot could do that. So all the way from detecting the corrosion to full repair without any human in the loop, but with humans able to have agency to what's working on. We've done a lot of work of transitioning this stuff into the Army, robots that have been able to go out and do work doing long-term surveys. And this one, you'll see us using the Android Tactical Awareness Kit to have one robot perform a survey, and whenever it came across a blue barrel, which we arranged in different locations around campus every day, all of this is fully autonomous. The second robot is deployed to that location with its lanthanum bromide sensor, able to work in that area. We were able to do this in rather crowded environments, as you'll see here quickly on the left. The robot, once it got done doing its radiation survey, was able to catch up with the other robot and get that working in that case. And then we got it up and working outside, and people back at a control center can track it. So these are designed to be demonstrations that take 40, 50 minutes, and we did them 10 days in a row. One of the things I'll just mention here is, just to finish up, is it's important for us to work in ROS, and we talk about trying to avoid silos. So when we actually develop these capabilities, we actually transition them into these software packages such as ROS DOE, or here you see the RTK working on actual vehicles supplied to us by the Ground Vehicle Science Center in the Army. And there you see the same situational awareness using full Silvus radios miles away with radiation sensors there. So that's kind of where we're able to go there. We've done some work. I don't think I have to talk too much about how AI is coming into place, but if you're interested in doing some work in that area, we have released some new gesture recognition sets for people actually wearing gloves, so that all the great stuff that you see out there with hand and gesture recognition can be done in glove boxes as well. And that's thanks to my team. And with that, I had to go a little fast, sorry, because of the technical hiccups, but hopefully that was helpful. So thanks, Adam.
Mitch, that was very impressive that you went that fast. And
I didn't give myself much choice, so.
Still covered it pretty well. I think we do have a minute or two to answer some questions. One of the questions that popped up was, what would be a typical level of radiation one of these robots may be able to see?
That's great. So most of our stuff is actually able to see fairly high levels of radiation, but at low energies. That tends to be what we see at Los Alamos. We've been able to work and consider the robots that would go into areas such as the H Canyon, which Leo talked about at Savannah River National Labs. And they can even survive for a certain amount of time, such as the Mighty Mouse did when it went into the White Sands to get the Cobalt 60 source. When we told Los Alamos that we wanted to put a robot in their glove box, they asked how much it would cost, and we said about $60,000, and that was referred to as, and as a university person, this shocks me, disposable. And then those robots are still running. So while some great work has been done, for example, at the Ohio State University and things like that, to look at radiation survivability in your typical nuclear environments, our experience is that as long as we're able to get our stuff running on commercially available robots that allow for quick replacement and repair and support, then we can see these things surviving long enough for them to be effective at their jobs.
Great. Where do you think AI might be able to push robotics?
That's a great thing. If you guys did not see it today, there's an excellent newsletter that came out of Los Alamos just today talking about uncertainty quantification and the use of VLAs, video language action models for robotics and LLMs. We've certainly used them. We have things where we can generate a set of low-level commands from a high-level voice command. Our robots have been said to go outside and check the door, go check the radiation levels by the window on the left, and the robots go and do it. We've been able to use AI for the data sets. The trouble is that these are really cool demos, but these black box models make it difficult for us to certify these things to be reliably used in all these situations. So I see AI as being extremely useful in solving subsets of the problems, such as AI recognition of gestures of people in gloves. I see it as a cool demo, but I love the work that is being done by A Division at Los Alamos to really understand how these things work and how you can certify them when using them in the broadest kind of high level senses. I would encourage people to go look for those news articles if they could.
That's great. All right, well, I would like to just go ahead and wrap it all up here. I really appreciate the presentation, Mitch. It's always good to see you.
Thank you
All
very
right.
much.
Just to kind of conclude, I appreciate everyone participating in today's webinar, and I look forward to the next version of it. Our next webinar should be scheduled for the end of the summer, and we're going to focus on national laboratory research and development within the robotics and remote systems field. So if you happen to have someone, or you are someone that's in the national lab environment and you're completing exciting robotics and remote systems design work, please feel free to reach out to me so that I can schedule you to be part of that panel. I would like to thank Mitch, Leo, and YZ for participating, and Dan for arranging everything for us, and everyone participating on the call today. Have a wonderful afternoon, and I'll see you at the next one.
Thanks, Adam.